And it's 10 a.m., so let's do it. Rise and Shine with Rob 101. Just curious if you've already done the Julia homework 2. If you could just indicate that in the chat so Tribby can see how fired up people are in class. How many of you have done the Rob 101 Julia homework 2? Raise our hands proudly. 2 of us. So 2 of us are members of the 100 variable club, okay? How many online? 0. 1. 6. Oh, okay. Well, 8 of the Rob 101 students are willing to admit that they've solved the 100 by 100 system of equations. Did you cry when you did it? No, because it wasn't that hard. That's what I mean. It wasn't painful. Solving the 10 by 10 when you had to step through it, and then when you had the 5 by 5 and you had to keep writing the equations differently, yeah, that was painful. But as soon as you got to the for loop, you're going like, wow. Okay, so I hope you starting to see the path that we're following to scale up mathematics. And you'll see it even more when we release Project 1 on Thursday at midnight plus 1 second or something like that. Is that it? Okay, bright and early Thursday morning, and then we'll talk about the project a tiny bit on Friday as well. So we were doing matrix multiplication. And the way we're doing it, it's all about dividing A into its rows, B into its columns, and then the way we get the ij entry of a matrix C, so if we let C be the product, we get the ij entry by the ith row of A times the B sub j column of B. And so you're always going like this, doing the multiplications and adding them up in your head. And that works for 3 by 3, maybe 4 by 4, and at 7 by 7, you're doing all these hand calculations on the side and trying to add things up, and it's just a nightmare for a human, but for a computer, it's just fine. The key compatibility condition is we can multiply A and B if the number of columns of A equals the number of rows in B. A is M by K, so M rows, K columns, and B is K rows by N columns, and then the product will be M by N, the way I've written it here. So normally, I even have in the matrix, this is N, and this is M, and I think now it matches what we have in the handout up there. So, if I do the product, I've got all these row vectors to multiply times column vectors. Row times column, as long as they have the same number of entry, I just add this one, this one, this one, this one. It's super tedious for big matrices, but easy for 2 by 2, maybe 3 by 3. And in Julia, you can extract the rows if you put whoops, don't want to mess that up. I wanted this one, I colon I, comma, colon, or otherwise you can do A, I, colon, and put an apostrophe, which takes, because Julia by default wants to do everything as a row, and Tribby talked about this in great detail last night in the recitation, and that apostrophe will do what's called a transpose and turn the column into a row. So you have 2 different ways of extracting the rows of A. Okay, so that's rows times columns. We can pause for questions of doing rows times columns. We'll do another example or two. But questions in the chat? At the very end of lecture, we took two matrices with the amazing entries 1, 2, 3, 4, 5, -2, 6, and 1. And in a blur of computation that you probably didn't have enough time to follow, we did A times B, and then we did B times A. So let's just mentally do, how would we get the 1, 2 entry, the 2, 1 entry of A times B? We need to take the second row of A times the first column of B. So then 3 times 5 is 15, and 4 times 6 is 24, and that adds up to 39. So that's how you get those entries, okay? And if you wanted the 1, 2 entry, you take the first row, second column. So then you have 1 times -2 plus 2 times 1, and that's 0. Okay, so you do the same thing, and you can put B on the other side of A, and when you do all those multiplications, the point is you cannot swap the order of matrices in general. You can't commute them. It's very important the order in which you multiply matrices. So very important that in general, A times B does not equal B times A. Now, very often, if A times B makes sense because of the sizes, when you change the order, the sizes may not work out, and so you can't even do it. So if you have a 3 by 2 times a 2 by 5, that gives you a 3 by 5, but if you do it the other way, the 5 by 2 and then the 3 by 2, it just doesn't work, okay? Because the 3 doesn't match with the 5. So in general, the sizes don't work, but even when the sizes work, the product A times B is different than B times A. Okay, so order matters. And that's very different than when we multiply numbers. We're very used to square root of 2 times pi is the same thing as pi times the square root of 2. Okay, so let's just do another example of matrix multiplication. I'm going to write down 2 fairly big matrices, and then we're only going to pick out a couple of entries of the product, because we're not going to do them all because humans get bored and professors get even more bored, okay? And you're probably as students going, well, we don't know that you're more bored than we are, okay? So, but we want to learn this skill, and it's going to be a really complicated matrix. 1, 2, 3, 4. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, okay? So that's 4 by 4, 4 rows and 4 columns. Okay, and let's do B. So how many rows do I want in B if it's going to be multiplying A? Yeah, it has to have 4, okay? So I'm going to let it have 2 columns, 7, 8, 5, 6, 3, 4, 1, 2. Okay. So now if I form C, and it's A times B, that is going to be what? So it'll be a 4 by 4 times a 4 by 2, and so that gives us a 4 by 2. Okay, so in the beginning, it's good just to check the sizes, okay? You can easily mess it up, but the key thing is this number, whoops. Come on, I selected U. Work. This number and this number are the same. The columns in A and the rows in B have to match up. If B had 3 rows, it wouldn't work. Had 5 rows, it wouldn't work. Anything other than 4, it doesn't work. And B can then have how many columns? As many as you're willing to write down, okay? You want to put 100 columns? Just don't bother me with it, but you can do it on Julia with no trouble whatsoever. Okay, so there it is. There's the matrix. What is the 3-1 entry in C? Okay, do the multiplication yourself while I'm writing some things down, okay? So just kind of quickly, can you just do this? Okay? But to be clear, it's A row 3 times B column 1. Okay, so in the beginning, it doesn't hurt to remind yourself which row and which column. Okay, so that's 9, 10, 11, 12. And we got the first column, 7, 5, 3, 1. And what did you get? Anybody get a number? I heard 158. That's the same number I got, so that pleases me no end, okay? Because I didn't check it on Julia, okay? I just, can you still do it? Okay, so that's how you do it. You pick out the row, and let's suppose we wanted to do C22. That would be A row 2 times B column 2 and 5, 6, 7, 8. I'm trying to do it on here where we can get some contrast so it's not blurring in, and we want the second column, 8, 6, 4, 2, equals so 5 times 8 is 40, and 6 times 6 is 36. We're up to 76. 7 times 4 is 28, and then we add 2, and I think we get 120. I'll put a question mark. You guys can check it under calculator, okay? But that's what you do, okay? So you go like this, literally, and you would go 5 times 8 plus 6 times 6 plus 7 times 4 plus 8 times 2. Because if we're doing exams, though we're not doing those in Rob 101, you wouldn't take the time to write down each entry as a row and then and do the columns. You just do this, okay? And then you say, I hope, okay? Okay. Are we good? If we have an entry to pick out, we could figure out which row of A and which column of B to do it. Any questions? Am I going too fast? Going too slow? Just right. You're never just right, okay? It's always too fast or too slow for somebody. So now let's do another example, which is kind of a weird one. but it's going to lead us into something interesting. Okay, I'm going to do A is 2 by 1, and B equals 1 by 3. I'll write some things down in a second. Okay, I can form this because it's 2 by 1, whoops, that's a 1, times 1 by 3, and so I get a 2 by 3. Oh, okay, what am I doing? I haven't written down A, but it's 2 by 1. It has 2 rows, 1 column. It's a column vector. B, it has 1 row and 3 columns. It's a row vector. What am I showing you how to do now? Multiplying a column vector times a row vector. And you're kind of freaking out, but let's remind ourselves all we need is the k's here to be the same. Okay, so I can take a column vector. So n can be 1 and k could be, I can take a column vector, n could be 4 and k can be 1, so it's a column vector. And I can take k to be 1, so b is a row vector, and m to be anything I want, and I can still multiply them. That's just a special case of matrices. All I've done is now we're taking that k to be 1. So let's see what this looks like, okay? It's kind of funny. So I'm going to write A as A1 and A2. And I'm going to write B as just B1, B2, B3. 1 by 3, so this is a 2 by 1, and this is a 1 by 3. So I'm allowed to multiply them using the rules of matrix multiplication. Ooh. So now I'm going to define C, by definition equal to A times B, and I'm going to get a 2 by 3 matrix. So what is the 1, 1 entry of C equal to? Well, it's the first row of A times the first column of B. Those are 2 scalars, A1, B1. What is the next entry of C? C1, 2. I still take A1, the first row, times the second column. And then what is C1, 3? I take the first row of A times the third column of B. Okay, it's really simple, and that's what makes it hard. It seems weird. We're thinking of rows, they should have lots of elements. We're thinking of columns, they should have lots of elements. But if I am a column vector, my rows have only 1 element, and if I am a row vector, my columns have only 1 element. So I can just multiply the 1 element and the 1 element. And so what's the next one? It's A2 times B1, A2 times B2, and A2 times B3. Okay, so Cij is the ith row of A times the jth column of B. That's it. So that's 2 by 3. Ooh. Had that feature turned off, and it's still there. Okay. So let's just keep that in the back of our mind that we now know how to multiply columns times rows. We started out our adventure of matrix multiplication by multiplying rows times columns. That's how we started. Really simple. Now we've turned it around. We knew how to do general matrices. Now I'm just looking at this really particular case when I take a column times a row, and then I build up a rectangular matrix in general. Okay. So, like Alice down the rabbit hole, we are starting down a road less traveled. Okay, so this is in chapter 4, matrix multiplication. Okay, so I'm going to give two matrices, using some of my favorite numbers. 1, 3, 2, 4, and then I've got 5, 3, I don't know why I do that, but I do. Okay, so we take, go away, the whole thing, do it right. We do rows of A, columns of B, okay? And I did this multiplication. Somebody will invariably check me, and hopefully I did it right. Okay, so you guys know to get the ij element, I take the ith row of the first matrix times the jth row of the second matrix. Okay, so that's the road we've already traveled, and that's how everybody does matrix multiplication. When I say everybody, I mean everybody, okay? No exceptions. Everybody does matrix multiplication that way. I'm going to teach you another way. Why? Because I want you to be able to factorize matrices, and that's not very common. Okay, so I'm going to do another one. Write this matrix down again. 1, 2, 3, 4 times 5, 3, 6, 4. And I don't have another color, so I'll just draw my boxes myself. And I'm going to divide this thing into columns instead of rows. And I'm going to divide this one into rows instead of columns. Yep, seems weird. So this is B1 row, and this is B2 row, and this is A1 column, and this is A2 column. Okay, so I want to give everybody a chance to get to this point, because we're going to do Shazam, something magic. Okay, we're going to do something magic here. Okay, so there's our matrix, and using our standard rows times columns. What I want us to do right now is to form A1 column times B1 row plus A2 column times B2 row. Okay, so get that. I'm going to have to cover up our result from doing the standard multiplication. But let's do this. So A1 column is a 2 by 1, and B1 row is a 1 by 2. I should get a 2 by 2 matrix. Okay, so what do I get when I do A1 column times B1 row? Well, I take 1 times 5, and then 1 times 6. Right? I take the first row of A1 column and I multiply it times the first column of B1 row. Okay, and then when I do this one, I take 2 times B1 row. I take 2 times 5, I get 10, and I take 2 times 6, and I get 12. Okay. I sense some confusion, so let me back up. Okay. When I'm doing a column vector times a row vector, this one is 1 by 3, but suppose it had been 1 by 2, then we would have only had this part. Okay, and so I take A11 times B1, A1 times B2, and then for this one times this one, it's A2 times B1 and A2 times B2. So that's how you multiply columns times rows for 2 by 2. Right, so if we do row times column, definition applied to this, here's the A1 row, here's the B1 column. We multiply them and add them up. It's a scalar. The 1, 2 entry is first row of A times the second column of B. So that's how it goes, okay? Seems a little strange at first. Now I'm going to multiply the second column of A. Second column of A times the second row.
Sorry, why did you get a 1 instead of 5?
Oh, that's a 5, yeah. 1 times 5, because I didn't do the full thing. I just said 1 times 1. It's a 5. Thank you. Maybe that's why everybody was staring at me, and they weren't confused about anything else. So someone in class pointed out very clearly that 1 times 5 is not 1. It's 5, except in Grizzle land. And then 1 times 6 is 6. 2 times 5 is 10. And 2 times 6 is 12. So that's our first entry. The next one, we do the second column times the second row. We do 3 times 3. Okay. We do 3 times 4. 3 times 3 is 9. 3 times 4 is 12. Now what's really sweet about this is the individual calculations. We're not having to do a whole bunch of addition at the same time we're doing multiplication. The bookkeeping is a little bit bigger, but that's it. Okay, so we're going to complete this. We now do 4 times 3, and then 4 times 4. Okay, 4 times 3 is 12. 4 times 4 is 16. Now we do the addition. 5 plus 9, that's 14. 6 plus 12, that's 18. 10 plus 12, that's 22. And 12 plus 16, that's 28. Okay. Seems weird and at the moment pointless, but let's check. Ta-da! They're the same, okay? And it's always the same. We will write that down. It's always the same, okay? So, you can do matrix multiplication, do this, and then you have to do a whole bunch of additions while you're multiplying this thing, but then you've got that one entry. And then you take that same row and the next column over and you multiply them all up and you add them all up, and then you got the next entry, you're done, okay? But you keep doing this and doing this and doing this, good chance of getting them all right. Okay, and Julia, it's not a big deal. I'm showing you another way. A lot of humans don't like this way because it's more bookkeeping, but instead of dividing the matrix into rows and columns, I do it as columns and rows. And then I multiply first column times the first row, and the second column times the second row, and this is the only time I do addition. Okay? And all of these, they're just multiplying two numbers and writing them down. Okay? 2 times 6, etc. Okay? So I'm just writing them down. So I do A1 column times B1 row, A2 column times B2 row. This one times this one times this one. Then I do A2 column times B2 row, this one. And so there's no addition to do until at the end, then I just add these all up. And it turns out to be completely equivalent to this. Okay, so if you want to blow the minds of your friends, teach them this, okay? But I wouldn't advise it to do it with your physics instructor, your other math instructors, or your chemistry instructors. 1 second, I wouldn't advise doing that. You'll be treated as weirdos and wrong, okay? Question from chat.
Is there a specific name for this method?
The question, yeah, is there a specific name for this method? No, we're going to call it our second method for doing multiplication, or alternative method. Okay, so here's what we're going to call it. Alternative method for matrix multiplication. Now, if somebody wants to give it a name, I guess, you could call this the column times row method. Okay. So I like the question. And in the standard way, that's row times column method. Okay, cool. Cool. So, now, I would not be filling your heads with 2 ways to do matrix multiplication unless this is going to have a huge payoff for us. So I promise you, it's worth the mental energy, not just so that you feel special, but because of what you're going to be able to do really soon. So here's the method. So we're going to partition A into columns. here's A, and we're going to write it as A1 column, dot, dot, dot. Here's the ith column, dot, dot, dot. And okay, so we'll assume this has n rows and k columns. And the vector AI column, that has n rows and 1 column, because it's a column vector. Okay, so that's n by 1. I want to keep track of the size. So instead of drawing the rows on A, we break it up into its column. Then we partition B into rows. Okay, so I'm going to write out B, and it'll have a first row. We'll figure out where it's going to end in a second. It's going to have an ith row, and then it'll have a kth row. Okay, so this is k by m. And so bi row, being a row vector, it has just 1 row. And since B has m columns, so does the row. Okay, this is bookkeeping. So partition A into columns, B into rows. We got that? Okay, I don't want to blow through this so quickly. Then we define C to be the matrix product, just like we've done 100 times. And the cool thing is C is equal to the sum I equals 1 to k of the ith column of A times the ith row of B. Does it have the right size? Let's just check, okay? Write that down. Let's just check the sizes. AI column times BI row is an n by 1 times a 1 by m. So that's an n by m. Yep. And then we add up n by m matrices. We keep n by m. And so C, just like we want it to be, is n by m. Okay, so n by m. Once again, it seems weird. Normal multiplication. We have to do all the additions in our head as we're going down here. Here, we're just multiplying entries, okay, very nicely, and we do all the addition at the end separately. And for humans, nobody likes to do it that way, okay? And there must be a really good reason, and we haven't gotten there yet, but it's coming. Okay, so let's just do this column times row method, as an example. So A, 1, 3, 1, 4, 2, 0. That's a 2 by 3. And we'll do B equals 0, 5, 1, 2, minus 2, 1. And then that is a 3 by 2. Okay, so let's figure out A times B. I'll let you write that down. I'll assume at home you're writing roughly the same speed as students in the classroom. I see most of the pens going down, except somebody's doing the multiplication ahead of me. Okay, so we have a cheater in the room. I can't tell if he's still writing down lecture notes or he's working ahead. I think he's working ahead. No, that's fine. I'm just teasing, okay? So how are we going to do this? We're going to take the first column of A, which is 1, 4, and multiply it times the first row of B, which is 0, 5. We're going to add to that the second column of A, multiplied times the second row of B. Okay? And then we're going to add the third column of A multiplied by the third row of B. So all the sizes work out. They're 2 by 1s times 1 by 2s. 2 rows, 1 column times 1 row, 2 columns. Okay, let's see if we're now getting better at these matrix products. 1, 4 times 0, 5. 1 times 0 is 0, and 1 times 5 is 5. 4 times 0 is 0, and 4 times 5 is 20. Okay. Next one. We just take 3 and we really multiply it times that row. So 3 times 1 is 3, 3 times 2 is 6. Now we take that row and we multiply it by 2. 2 times 1 is 2, and 2 times 2 is 4. So you just have to do a few of these and you get warmed up. We take 1 times that row, so we get minus 2 and 1, and then, whoop, come back. You got too excited. 0 times that row, and we get 0, 0. Okay, and then we just add these guys up. 0, 3 minus 2 is 1. 5 and 6 is an 11, as 1 is 12. 0, 2, 0 is 2. And 24 and 0 is 24. Okay? Seems weird, given the other way of doing matrix multiplication. Totally weird, okay? Okay, so this is, by definition, C. So let's do C21 by standard multiplication. Okay, so I'm going to do C21. So it means we need the second row of A times the first column of B. Okay, so it's going to be off the screen, so I have to write it down here. And I have it in my notes, but it's A2 row times B1 column. Okay, so this is the way you know and love. And you can't see that, but I'm copying it down from what it was. We're just checking to see that I'm not lying to you, that we're going to get the same thing as we did with the alternative method of multiplication, okay? We're just checking. Okay, so now we have to do this and add them all up. Okay, well, I chose numbers where it's not too hard. 4 times 0 is 0, 2 times 1 is 2, and 0 times minus 2 is 0, so that is 2. So the C21 entry is 2, whoops, and that's correct. Okay? Questions? Because I'm going to set us up for awesomeness, okay? We don't want to be set up. That sounds bad, okay? No. Okay. I'm going to set you up for more of the road less traveled, okay? So you don't have this, but it's, I will add this stuff to the book, and this will be pasted into the lecture. I don't want you writing anything down. Stop writing, just listen. Stop writing. I mean, you can do what you want, okay? You're adults, and I have no power over you. You can write if you want, but I suggest you don't, okay? So here's the thing. I've got a matrix, A, 3 by 3 in this case, and we want to solve AX equals B, and then I give you a B, okay? And I think this would be the normal response. I mean, very doable, but just kind of painful. And if this had been 17 times 17, you would have said, forget it, okay? You're not paying me enough to make me want to do this, okay? So I get it. Now here's what I want you to think about, and this is really pay attention. Suppose we knew how to write A as a matrix that's lower triangular times one that's upper triangular. So here's my diagonal. I'm 0 above it, and I've got other junk, so it's a lower triangular matrix. Here's my diagonal here. I've got zeros below it, and I've got other stuff here. So it's an upper triangular matrix. Suppose I knew that A was the product of a lower triangular matrix and an upper. It's called LU factorization. They're factors, just like you take numbers and multiply 12 as 3 times 4. Those are factors. I've taken A and I've multiplied, I've divided it up, factored it into a lower and an upper. We don't know if we can do this very often or anything. And the question is, can we use this to our advantage? And so let's write the equation AX equals B with A as L times U. Okay, so here's A. So that's AX equals B. This guy is unknown. So the product is an unknown as well. So I'm going to call that Y. Okay, so this becomes Y. So I rewrite the equation like that. So here's my Y. And then I do it like this, okay? So now I have the equation L lower triangular times Y equals B, and I've just run out of time, so I'm going to cheat and go a minute or two over, but no more than that. But this is a lower triangular matrix, and you guys just go, ta-da, I solve for Y1, I solve for y2, I solve for y3. Trivial problem there. Okay. Well, now I just solve ux equals y for x, and that's an upper triangular problem. So that's back substitution. You didn't do much of that in Julia homework 2, but it's just the same thing, okay? You start at the bottom and you go to the top. And so you eat that one alive, and then you've got the solution to your overall problem with 2 back substitution, if you can factor A into a lower and an upper. So, painful, painful, simple, whoops. This one is simple, ux, and then this wasn't as simple. 1 painful problem, 2 simple problems, and this scales to 1,000 by 1,000 matrices. That's the point, okay? So that's where we're going on Friday. Sorry to be going over.